Hello everyone, welcome back to the NPTEL course on materials informatics. In today's lecture we will be discussing the topic of machine learned interatomic potentials. Okay. So, just as a recap, so far we have completed 2 modules in this course. So, in the first module we sort of looked at the basics of machine learning, simple regression classification models and so on. We looked at both sort of classical machine learning models as well as more advanced neural network based models. We also looked at the principles of convolutions and also how they can be adapted in graph based networks which are used in modern machine learning architectures for modeling materials. In module 2 we went a little back in time. So, we looked at physics based models and physics based calculation techniques which provides a lot of the data for most of the machine learning models that we train. So, we looked at principles of density functional theory, we also looked at molecular dynamics a little bit and then principles of statistical mechanics, how that is used in both lattice models, construction of lattice models as well as in sampling techniques, right. So, we looked at all of these in module 2. So, with today's lecture we are beginning module 3 which is basically advanced topics, right, and the first part of the advanced topic module is basically machine learning interatomic potentials, which is the sort of theme of today's lecture. The schematics that I am going to be using through this lecture come from various sources and they are highlighted in the corresponding slides. Okay. So, the first question is why should we bother about interatomic potentials, right. So, the key thing to note is that interatomic potentials help us simulate fairly large length scales or long time scales, right. And if we look at phenomena that are quite common in materials, we have to worry about things that happen of the order of picoseconds and to things that happen of the order of microseconds and probably even years, right. But when it comes to let us say phase transitions or motion of dislocations, for example, so plastic deformation or some kind of magnetic transitions that happen within materials, they generally happen at time scales of nanoseconds or larger, right. So, nanoseconds to microseconds to milliseconds. So, with physics based models, so if you think about solving the Schrodinger equation using density functional theory and calculating properties, dynamic properties of materials, that is sort of not very feasible. It is not feasible even to achieve nanoseconds with density functional theory based molecular dynamics or even nanometers. So, you are sort of restricted to few angstroms, maybe a nanometer or few nanometers, not definitely not hundreds of nanometers, and in terms of time, time you are probably accessing a few hundred picoseconds, right. So, this is where sort of interatomic potentials can help, because classically and these interatomic potentials are also called classical force fields. These potentials or force fields have simple functional forms, so they are not. So, you do not have to solve the Schrodinger equation every time. The energy and its derivative, basically the force, come with very simple functional forms whose evaluations is fairly quick. So, which implies we can simulate larger length scales. So, we can go slightly beyond nanometers, hundreds of nanometers and so on, and we can reach nanoseconds or beyond nanoseconds in terms of time. So, this gives us access to studying phenomena that happen at these larger length scales, right, like movement of dislocation, stacking faults, adsorption of molecules on surfaces, forming of clusters and so on. So, larger length scales and also longer time scale phenomena. So, time scales that are longer than simple atomic hops, right. So, that is why interatomic potentials are useful. And as I mentioned before, interatomic potentials are quite useful in studying interfaces which are large scale systems. Interfaces are usually of the order of nanometers, several nanometers to micrometers. Understanding diffusivities over larger length scales, right, and then also understanding some kind of rapid fast phase transitions. I mean, think about sort of amorphization or sort of glass formation instead of crystallization. So, that is a rapid phase transition. This can be studied using interatomic potential based molecular dynamics, which can in turn help us in constructing some kind of metastable phase diagrams. And the key difference, one of the key differences between interatomic potentials and lattice models. So one is lattice models are energy models, they are not really potential, so you cannot really differentiate these lattice models to get forces. But interatomic potentials you can. So you the functional forms are fairly straightforward. You should be able to take a derivative and you should be able to calculate forces as well. So they actually model interactions. Interatomic potentials actually model interactions between different atoms in a structure, whereas in lattice models it's a screened contribution to the overall energy, right. So a pair contributes in an averaged way to the overall energy compared to other pairs, other triplets and so on. So this kind of screened average interaction, interatomic potentials is the bare interactions, right. And the other important thing to note is that in lattice models generally the underlying structure cannot change. So the lattice is fixed, whatever motion of atoms we have we coarse grain, so we do not consider the motion of atoms as long as they are in the vicinity of their high symmetry positions. But in interatomic potentials the underlying structure can change, so the atoms can actually move, which implies we can deal with structural polymorphic transitions and so on. And as with any computational tool, technique, model, you always have the cost accuracy trade off. So the more complicated an interatomic potential is, so the more complex the mathematical functional form is, the cost of evaluation goes up, which implies the model becomes slower to run, but its accuracy also goes up. Right. So it can reach closer to what we refer to as ab initio accuracy or DFT accuracy, because in DFT you get the properties directly from the electronic structure. So if our potentials are as accurate as DFT, then we are basically very close to quantum mechanics, and hence our prediction should be quite reliable, right. And these plots basically show you examples of potentials that are that are being actively used. One of the famous potentials is what is referred to as the Lennard-Jones potential. So this was developed almost a century back, and as you can probably see, this potential has a very simple functional form. So you have U of r, so U basically stands for the energy. Energy of a given atom as a function of its distance, right. So it has this simple functional form. So there is an epsilon term and the sigma term. So epsilon and sigma are fittable parameters. You typically use some experimental data to determine both your epsilon and sigma. So sigma by r power 12 basically stands for some kind of a repulsion term. So as atoms approach each other very closely, right, so they will start repelling each other because of both electronic repulsions as well as nuclear repulsions. So you cannot compress atoms beyond a certain extent, so that is why there is a huge repulsion term here, and the sigma by r power 6 basically stands for this kind of an attraction term. So as atoms are far apart, they are naturally attracted towards one another, right, and the balance of this repulsion and the attraction terms normally leads to some kind of a minimum in your potential energy surface. So this is roughly the U of r here, and this is roughly the distance r here. So you sort of get a minimum, and that minimum basically represents your sort of equilibrium bond length, or in the case of solids your equilibrium lattice constant. Right. So and even though Lennard-Jones potentials sort of appear very simple, so there are only two parameters that are used to model this potential, so the epsilon and the sigma, it's still quite useful. So this is a study of diffusivities in on a surface, that was using Lennard-Jones potentials as recently as the last decade. And interatomic potentials can also be used for modeling surfaces, interfaces here, and also interfaces with some kind of adsorbates and so on. So these kinds of models are quite useful in the field of catalysis and electrochemistry. So all in all, interatomic potentials sort of model the potential energy surface of a given material. So this U versus R plot is what we refer to as the potential energy surface of a given material, and we want to model these potential energy surfaces as accurately as possible, so that we can get dynamic properties as accurately as possible. So now that we have motivated interatomic potentials, the next question is why add machine learning to these interatomic potentials. So the straightforward answer is classical force fields generally have difficulties in modeling very complex potential energy surfaces. So for example, let us say I have two different potential energy surfaces for two different systems here. So I have E versus V. V stands for volume. You can consider this as a proxy for your bond length, right. So you have energy versus volume curve. This curve sort of looks mostly parabola like, right. So it is mostly parabolic here, and then there is some sort of tail that is starting to appear here. This is a fairly simple functional form. This is very similar to the Leonard-Jones functional form that we saw in the previous slide. So this kind of a potential energy surface can be accurately modeled using a using a classical interatomic potential. But let us say your system has a very complicated potential, right, a potential energy surface that sort of looks like this. So you see that there are local minima here, and there is also a global minimum here. So the global minimum looks parabolic, that is fine, but there are also local minima here which may be important for modeling this system. And this type of a potential energy surface is sort of difficult to model with a classical force field, right, because we have a fairly limited functional forms that are available. There are very few systematic ways of improving the accuracy by adding in more and more sort of terms on a basis set. I mean that is possible, but if you do that, then you are sort of increasing the computational cost. So classical force fields have limited sort of functional forms, mathematical functional forms, and hence their accuracy is limited, especially for systems that have complicated potential energy surfaces. There is also other limitations with classical force fields. So typically the parameters that you need to fit in classical force fields, you either rely on experimental data or computed data, so something like a DFT based calculation for smaller systems, and hence they can have transferability limitations. So let us say you fit a classical force field for a copper surface, right, or for a bare copper surface. That force field may or may not work when you have copper surface with an adsorbate, right. So the adsorbate can be a carbon dioxide molecule or an oxygen molecule or so on, right. So just by adding another species you can sort of break how well the interatomic potential actually works. So classical force fields have sort of several limitations, both mathematical as well as physical limitations. So this is where sort of machine learning plays a role or can contribute, because when you add in machine learning, you sort of increase the mathematical functional complexity that can be present in your interatomic potential. So this in principle can or should be able to handle a wide diversity of species and also different bonding environments. So in the same structure, if you have ionic, covalent as well as metallic bonds, your machine learning interatomic potential with its flexible functional forms should be able to capture all these, but a classical force field may have difficulties. And with machine learning interatomic potentials, you can also introduce what we refer to as permutation and rotation invariance or equivariance. We will sort of touch upon these concepts a little later in the upcoming slides, but basically permutation invariance stands for the fact that if you sort of exchange two atoms in a bond, the energy of that bond itself should not change, right. So that is sort of referred to as permutation invariance. And rotation invariance is if you start rotating structures, right. So the energy of the structure should not change, right. So if you have a cubic structure, you rotate that structure by 90 degrees, suddenly you should not get a different energy, right. So that is referred to as rotation invariance. We will sort of touch upon these concepts a little later, but with machine learning interatomic potentials, you can introduce these concepts or these ideas in a more systematic fashion compared to classical force fields. And of course, because of their flexible functional form, they can have improved accuracy, especially against density function theory calculations on which these interatomic potentials will be trained. So DFT will once again provide us the training data, but you can get higher accuracies against your training data compared to what classical force fields can achieve, right. So these are the sort of benefits with introducing some machine learning within our interatomic potentials. So to sort of visually understand what we try to do with our machine learned interatomic potentials, basically we let's say we have an atom of interest. So let's say that atom is sitting here. We sort of draw a sphere of influence around the atom. So I am showing a projected view here, right. So the atom of interest now will have other atoms that are bonded to it within its sphere of influence, right. So we now find a way to fingerprint how this bonding environment looks like for this atom of interest. So how many bonds it forms, what types of bonds it forms, and what type of species are present within this bonding environment, right. So we try to fingerprint this bonding environment, and once we have successfully fingerprinted it, we can then repeat this process for all the other atoms that are present in the structure. So after this fingerprinting exercise, we can then pass the set of features or the set of fingerprints that we have generated through some kind of a machine learning framework. The framework is up to us, so we can decide whatever machine learning framework we want to use, and once we use a machine learning framework, the resultant prediction that we get is basically the sort of energy of the underlying structure, or if you are only worried about an atom of interest, then it is the energy of that atom within that structure, right. So the output prediction is basically your energy. You can also take derivatives of this energy and get forces, so you can also calculate forces around this atom of interest, right. So in very simple terms, in machine learning interatomic potentials, we have an atom of interest, we draw a sphere of influence around it, and we fingerprint the local environment around that atom, and then we feed that fingerprinting exercise. So when we fingerprint, we get a set of features or a set of embeddings, we feed that into a machine learning model, and the resultant model that we get is basically our machine learning interatomic potentials. And this is how the classic machine learning interatomic potentials were actually constructed, right. So the more modern ones use more graph based neural networks, and the more classical machine learning interatomic potentials, which were all constructed in the last decade, so from the 2010s to or even late 2000s to 2010s. So the machine learning potentials that were constructed were we can sort of call them as classical potentials, because they sort of have this general idea. So you do a fingerprinting exercise, generate a set of features or embeddings, and then you pass it on to a machine learning model, right. The modern ones we will touch upon a little later, they use more graph based techniques to construct machine learning interatomic potentials. Okay. So let us take a look at classical machine learning interatomic potentials first, and try to understand how these work, which will then help us understand how more modern machine learning architectures, MLIPs sort of work. So the way the classical machine learning interatomic potentials work is that, so let us say you have a structure, so once again you identify an atom of interest, you draw a sphere of influence around that atom, and then you sort of fingerprint this local environment, right. So the fingerprinting exercise is, there are several different choices that we can exercise in how we construct these fingerprints, these embeddings or these features. So but once you generate these fingerprints, we then go through a simple regression exercise, right. So the regression during training is basically against reference DFT data. So we should have had DFT calculations performed, which will then be used to train this model. If the model is already trained and it is doing a production run, then it will do this regression exercise to basically get an atomic energy, so energy of this reference atom, right. So you get an energy for a given atom, right. You repeat this exercise for all the atoms, right, and you do a simple summation, and you basically get your final potential energy surface or the final energy of your underlying structure, right. So if you keep changing the underlying structure, so you introduce perturbations, you introduce modifications within this underlying structure, you basically get energy as a function of bond lengths or volumes, which is basically your potential energy surface, right. So the overall energy of your system is basically a sum of atomic energies, and each atom or the energy of each atom, we sort of decompose that into its local environment, right. So the atoms to which it is actually bonding. So in practice, how do we do it? So we generate a lot of DFT data first, so that basically is our reference data set which we use to train our model. We then train our model, right. So this may be the actual sort of exact potential energy surface, but that may be unknown, but we may have points in between, right, that we have calculated using our DFT. We then fit our model using the structural descriptors or features that we generate, and hopefully we get a very close imitation of the actual potential energy surface. So how are so if you think about this reference data set, right, so how are these typically trained? So what is present in this reference data set? you typically have a bunch of total energies and atomic forces as well as lattice stresses that you have calculated with the DFT on a bunch of different structures. So the structures can have different compositions, they can have different configurations, they can have different defects, they can also have different geometries. So you can take the same composition and put it through a cubic geometry, an orthorhombic geometry, a triclinic geometry and so on. So they can also have different geometries. So you try to generate as diverse a data set as possible that is relevant for your system, and then you try to train your model to capture the potential energy surface. So what are some of the popular classical machine learned interatomic potentials? So you have the artificial neural network potential, which was one of the older ones that was developed around 2007, and then you have what is referred to as gap or Gaussian approximation potential, then you have moment tensor potentials, and then you have SNAP, which is spectral neighbor analysis potential. So these four are more popular ones. And let me just break down how these different potentials that I described in the previous slide are constructed. So these are some of the popular classical machine learning potentials. So moment tensor potential or MTP, spectral neighbor analysis potential or SNAP, and then you have Gaussian approximation potential or gap, and then you have the artificial neural network potential or ANNP, right. So these are the popular classical sort of machine learning interatomic potentials, and I'll just break through or break down what is the key idea behind these potentials, what kind of descriptors or fingerprinting exercises that these potentials do to capture the local environment. How do they actually train the model? So what type of training algorithm do they use, and what type of basis functions do they use to describe their descriptors? So typically the descriptors is expanded over a bunch of basis functions, so we will also see what type of basis functions they use. So in terms of moment tensor potentials, so the key idea is that you break down or you capture many body interactions, at least 3 body interactions via moment tensors. So we will see what moment tensors are shortly. So the descriptor that they use to capture their the local environments are basically moment tensors. Training algorithm is this is BFGS. So BFGS is a very popular sort of optimization algorithm that is used by a lot of researchers. And then the basis functions that they use to expand their moment tensors is Chebyshev. The Chebyshev basis functions are used for expanding the radial component. And then you have SNAP. So in SNAP you basically project your local atomic density. So local atomic density is basically the distribution of atoms or the density itself. How is the density varying within the sphere of influence? So the variation of density basically tells you how atoms are distributed, right. So where are they located within your sphere of influence? So one can calculate this local atomic density in a fairly trivial fashion. So you just need to construct a sphere of influence around an atom, and then wherever you have atoms you will have high densities there, and in the other regions you will have low densities. So this local atomic density can be calculated quite easily. So once it is calculated, it is then projected on 4D hyperspheres. So 4D stands for 4 dimensional. So generally we sort of deal with 3 dimensional spheres or 3 dimensional systems, but when you sort of project your local 3 dimensional variable into a 4 dimensional hypersphere, that sort of gives rise to a lot of computational advantages. And using Fourier transforms and so on. So that's why the developers of SNAP use this projection technique, and once you project it on the 4D hyperspheres, you can then describe your local atomic sort of environment using what are referred to as bispectrum components. So think of these are Fourier transformed versions of your 4D hypersphere. They use a simple linear linear regression or linear training algorithm, linear optimization algorithm, and the basis functions that they use for describing these descriptors are basically hyperspherical harmonics. So spherical harmonics are in 3 dimensions. If you generalize that to 4 dimensions, you have hyperspherical harmonics. So in spherical harmonics you typically have 2 different angles along which you sort of expand on. So you have the sort of polar angle and the azimuthal angle. In hyperspherical harmonics you have 3 angles. So that is the main difference between spherical and hyperspherical harmonics. and then you have Gaussian approximation potential. So here once again you calculate the local atomic density, but then you model this atomic density, or you sort of project it on what are referred to as smooth overlap of atomic positions, or basically a bunch of Gaussians, right. So your descriptors are basically weighted sum of Gaussians. The training algorithm itself is what is referred to as Gaussian process regression, and the basis functions are bunch of Gaussians as well as spherical harmonics. And then you have the neural network potential. So here you have a local environment which is sort of expanded via radial and angular distribution functions. So these distribution functions sort of give rise to a set of features or set of input nodes, right, that you have for a given structure. You then whatever features you generate, you pass it on to a feed forward neural network. So that is the key idea behind artificial neural network potentials. These potentials use a limited memory BFGS algorithm for fitting, and they use Chebyshev polynomials for expanding the radial component and also the angular component, if I am not wrong. Okay. So this is sort of the breakdown of the classical machine learning potentials. So what is the key idea, what type of descriptors they use, training algorithms, basis functions, and so on. We will take a deeper look at the moment tensor potential in the upcoming slides. But once you understand moment tensor potentials, it is sort of easier to extend that understanding to other potentials. So snap, gap, and AN and P. Moment tensor potentials gives us a nice mathematical framework to understand how the fingerprinting exercise is done. And just to summarize some of the strengths and weaknesses of classical MLIPs, machine learned potentials. Typically these are easy to train, so they do not require a lot of computational resources to train apart from your DFT calculations. So the DFT calculations to generate the training data set is a fixed cost. So that you will need to that you will have to spend irrespective of which potential you are using. So you will always have to generate a training data set. But once you have a training data set ready, these potentials, the classical machine learning interatomic potentials, are easy to train. So they train quite quickly. Typically they train on CPUs, so they do not require very advanced GPU architectures, and they are also fast to run. So once again you can use CPUs to run them in sort of production mode, and they are sort of reasonably accurate. So whatever system you are trained, you can achieve fairly good levels of accuracy, but these potentials typically do not generalize well. So if you have trained for example machine learning potential on a specific system, so that could be sodium chloride, you cannot expect that that moment tensor potential to suddenly do well on cesium chloride or potassium chloride, right. So you will have to retrain, and when you retrain you may lose the accuracy on the original system that you had trained your moment tensor potential on. So they typically do not generalize well, these classical MLIPs. They are also short sighted in the sense that they only understand interactions that happen within a sphere of influence around a given atom. Right. So if you have structures that have long range interactions, graphite is a classic example which has van der Waals interactions, then these potentials will have limitations on their accuracy. They also have poor learning rate. So what I refer to learning rate, this is not a hyperparameter. What I mean by that is for a given level of accuracy they typically need large amounts of data. So if you want close to about 5 to 10 millielectron volt per atom accuracy on energies, all of these potentials you may need about 5000 to 10,000 DFT calculated data points. So they will require large data to reach a given level of accuracy. And the other thing is they typically do not scale very well with number of elements. So let us say you have a binary system, these potentials could run fairly quickly on a binary system, but let us say you now have a ternary system or a quaternary system, so you have more number of chemical components in your system, then these potentials become significantly slower. So the more chemical components you have in a system, typically these classical machine learning potentials become much slower with increasing number of components and number of elements. It does not hold true for all the potentials, but many of them suffer from this poor scaling issue with number of elements. So if you have let us say a high entropy ceramic or a high entropy alloy system which has let us say 7-8 chemical components, then many of these potentials may suffer from poor speed. So they may actually not be significantly faster compared to doing even density function theory based calculations. Okay. So with this breakdown of classical machine learning interatomic potentials, let us take a closer look at the moment tensor potential. Okay. So what is the moment tensor potential, right? So so you sort of write, so this is basically energy of a given configuration of atoms, so energy of a given structure. MTP basically stands for the prediction from moment tensor potential. So this is the quantity that the potential is trying to predict, the energy of a given configuration. As with any other classical machine learning potential, it tries to write that as a sum of individual atomic energies. So V basically stands for you know, a smooth function, right, and Ni basically stands for a given atomic environment. So I is basically corresponding to a given atom, right. So you basically calculate the energy contribution of a given atom or the atomic energy and then sum it over all the individual atoms, right. So once you do this sum, you get the overall energy, and this is the underlying principle of all you know, classical MLIPs, right. So the function V is sort of constructed in such a way that, you know, it is sort of invariant to permutation. So if you exchange atoms in a given sphere, you suddenly do not get very different energies. It is also invariant with respect to rotations and reflections. So if you rotate a structure, you will get the same energy. So if you take a cubic structure, rotate it by 90 degrees, you will get the same energy for the cubic structure, and also reflection. So if you have reflection, you know, if you take a structure and have a reflection of that structure, you know, if you feed it in as an input, the output energy will still be the same. So how does this you know, individual atomic energy term look like? So you can probably see that, you know, it's a linear function of some weights, right, indicated by zeta here, and then B alpha terms here, right. So B alphas, you can sort of consider them to be your descriptors, right, descriptors of your local atomic environment, and your zeta are basically the weights, right, which are learnt or which are fit to a reference data set, right. So when you are learning your moment tensor potential, you will learn these epsilon terms, so you will learn the zeta terms, right. And this B alpha term is basically your fingerprinting of your local atomic environment, and these are written in terms of basis functions as a summation of or an expansion of basis functions, and these basis functions are expanded or written up to a maximum level of contracted moment tensors. So I know this is a mouthful, so let us break it down one by one. So what do we mean by moment tensors here, right. So basically you fingerprint your atomic environment here, local environment, through what are referred to as moment tensors. So what are moment tensors? So for a given atom here, so given atomic environment here, right, we sort of describe our moment tensor as basically a summation of all the other elements within the sphere of influence of this atom I, right. Of all the other elements within the sphere of influence, we basically refer to this moment tensor as a product of two terms. One is what we call a radial term, a radial component, and the other is an angular component, right. So this radial component basically indicates how each atom j or how far is each atom j from the central atom of interest I here, right. So you take the modulus of the relative distance between the two atoms, right, and Zi and Zj are basically the atomic identities here, right. You can think of these as atomic numbers and so on, right. So basically the radial component tells you how far the other atoms are given a reference atom, right. And the way we typically write this radial component is that we in turn, so we take this radial component and in turn expand this using a Chebyshev polynomial basis set, right. So you may have a discrete number of bonds here, discrete number of Rij's. We are basically projecting those Rij's as a continuous function or a summation of Chebyshev polynomials, right. So these Chebyshev polynomials have standard mathematical forms. You take polynomials up to an order of beta here, so that is a hyperparameter that you will have to choose, and then the C terms are basically the weights assigned to each of your Chebyshev polynomials, and these weights once again will be determined during the fitting process. So you see that there are two sets of weights that will be, so the zeta terms and the C terms, that will be determined during the fitting process, right. So so moment tensor consists of the radial term, it also consists of the angular term. Right. So the radial terms is simply bond distance, the angular term is basically referring to the orientation of atoms within a given sphere or within a given bonding environment, right. So the way these angular terms work is we take outer products of the vectors that connect the central atom to one of its neighboring atoms. So Rij is basically your vector, right. So it has Xij, Yij and Zij. So if you take the outer product, you start basically getting a tensor. Right. So this is the Frobenius product. So you get a tensor here, and these tensors basically encode angular information, right. So if you do Rij and Rik, for example, you now can encode 3 body interactions. So the angles between your Ij bond and the Ik bond, so you are basically accounting for that angle Ij and Ik here. So you are basically accounting for 3 body interactions, right. So the more complex your outer products are, the more many body interactions you can actually take into account, but your potential will also become more expensive, because taking these outer products requires matrix operations which can become expensive. And a simpler way to understand this angular component is that you know, if you do not take any product, right, so this just a scalar, so you just take the, let's say, the modulus of Rij, that's just a scalar. If you just take the Rij as is, that's a vector, and if you take one Frobenius product, one outer product, that basically gives you a tensor. Right. So starting with simple vectors, you start getting more and more complicated tensors, and that's why these objects are referred to as moment tensors. So they have in some amount of bond distance information, right, which sort of contributes to moment in some sense, and they have the angular information in the form of tensors, right. So once you have these moment tensors, you can also find ways to contract them or make these tensors more sparse, right, or flatten these matrices. So those are basically your contracted moment tensors. So you can do mathematical operations to determine which moment tensors are important, which moment tensors are not. So the contraction operation is fairly straightforward. But then you have to define what is referred to as a level of your moment tensor. So when you write a moment tensor, you have two variables here, mu and nu here. So mu basically stands for the complexity in your radial component, and nu basically stands for the complexity in your angular component. So the combination of these, so how complex you want your radial and your angular components is basically compiled in this complexity term called level. So that's what is referred to as level of your moment tensor, and the level of the moment tensor is given by the simple expression here. Now this expression can be changed, right, but the original developers of moment tensor potentials use this expression. So it's 2 plus 4 mu plus nu. So given a maximum level, so let's say you want a level of 12, for example, you can have several different moment tensors that are contributing to this maximum level of 12. Right. So you specify a level, so the level is basically a hyperparameter that we specify during training of our potential. So once a level is specified, the moment tensor potential sort of determines which contracted moment tensors are important, and then assigns weights to both the radial component and to the overall moment tensors itself, right. And that's how it gets the energy of a given atomic environment, and then you take a simple summation over all atomic environments and you get the overall energy of your configuration. Okay. So how is the fitting process done? So you have the energy that is being predicted by the moment tensor potential for a given configuration K here, right. We can then reference that energy with a reference energy, which is usually obtained by quantum mechanics, such as density function theory based calculations. You can minimize errors on energies, you can minimize errors on forces, right, and you can also minimize errors on stresses, or you can minimize errors on all of them with some associated weights, right. So these W terms are basically hyperparameters that we can choose to decide whether energies are more important or forces are more important or stresses are more important, right. So and then in sort of minimizing this quantity here, right, we are basically minimizing the root mean squared error or the mean squared errors on the energies, forces as well as the stresses here. So basically when you fit your moment tensor potential, you are trying to minimize errors on energies, forces and stresses with some corresponding weights assigned to them, and you do it for all the configurations present in your training set. So if you have 1000 configurations, you calculate the errors across the 1000 configurations and you try to minimize the errors by updating your sets of weights. So the weights are indicated by theta here, which is basically a collection of your zeta terms and your c terms, right. So you can also sort of visualize moment tensor potential in a kind of a neural network type form here, but keep in mind that moment tensor potentials are not neural network based. So in that sense they are not a very modern kind of an architecture, they are still quite classical and still they carry a lot of physical intuition within how the model is actually constructed. Okay. So just a couple of notes. So once a moment tensor potential is fit to some reference data, it can be used for both the static and dynamic runs. So the package that is most often used for both static and dynamic calculations, molecular dynamics, is LAMMPS, and there are ready-made wrappers that are available that allows you to use moment tensor potentials with LAMMPS. And this kind of exercise is quite common in other machine learning interatomic potentials as well. Even the more modern ones which use graph based networks, you almost always tend to use LAMMPS to do both static and dynamic runs. And moment tensor potential specifically can also or also has active learning incorporated into it. So active learning is where the model basically evaluates each configuration that it is generating. So this could be during molecular dynamics. So in molecular dynamics you keep perturbing your configuration and you try to calculate the energies and forces at a given configuration. So whenever you generate a new configuration, moment tensor potential can basically evaluate whether the configuration falls within a certain extrapolation grade where it is confident in its predictions, right. If it is confident in its predictions, then it continues to do the dynamic simulations, but if it is not confident, then it has the ability to stop and let the user know that it is not confident of making predictions on a given configuration or a given structure. You can then take that structure, do DFT calculations, refit the moment tensor potential, and then proceed with the original calculation. So that is the typical workflow in active learning, and moment tensor potential has active learning built in, so it is easy to incorporate with existing density function theory or LAMMPS workflows. Yeah, so those are some of the sort of nice things about moment tensor potentials that we should keep in mind. And just as an example of how moment tensor potential is used in practice, right. So this is an example of predicting migration energies, so or migration barriers. So how easy it is for lithium to move in several different solid electrolyte or lithium containing compound materials here. So all of these all of these predictions were compared against experimentally measured barriers, and you see reasonably good agreement between predictions of moment tensor potential and what is experimentally measured. This is work that I was actually involved. So we try to characterize how well lithium actually moves across an interface here. So you have a lithium phosphide lithium interface and lithium phosphide different lithium phosphide and lithium interface here. These interfaces are very important when you consider lithium based solid state batteries. So that is why we wanted to model lithium transport along these interfacial systems. These interfacial systems are quite large, so that is why we used moment tensor potentials for modeling these systems. And this is another example of an interfacial simulation involving moment tensor potentials where the authors try to simulate a silicon silica interface, right. So this is silicon and then you have silica in between, and they try to model the sort of stability and transport across the silicon silica interface. So with that we will have a short recap of what we discussed in this lecture, and we will take a stop. So interatomic potentials are important for simulating dynamics in several systems, and machine learning interatomic potentials can improve upon the accuracies of classical force fields and can have similar computational costs. So you can access larger length scales and longer time scales at better accuracies than what is possible with classical force fields. The classical version of the machine learning interatomic potentials or classical MLIPs are all atom centered, right. So they try to obtain energies for a given atom in a structure, and then they sum up those energies to get the overall energy of your given configuration. So the classical MLIPs, their accuracy sort of largely depends on how well they do feature engineering. So how do they fingerprint the local atomic structure and whether or not they include non-linearity in their model or in their fitting process. We looked at moment tensor potential specifically. So these fingerprint local environments using what are referred to as contracted moment tensors. So each moment tensor has both radial and angular interactions built in. So it does capture some many body interactions, right. So and we also looked at how MTPs are fit and examples of where they were used in practice. And there are some limitations of classical machine learning interatomic potentials. They do not generalize well, they have poor learning rates, and they do not scale that well with number of elements. And the key to solving all of these problems is by using graph based neural networks, which is what we will discuss in the next lecture. So with that, I thank you all for joining today's lecture, and I will see you all in the next one.